have Dr. Łukasz Pawela from Gliwice. So he did his PhD in Gliwice, and then he was a postdoc in Kcik, in Gdańsk. And now he's back in Gliwice, as I understand.
Yes.
And today he will tell us about distinguishability of quantum measurements. Yes.
Okay. So thank you for the invitation. Thank you for the introduction. It's always a pleasure to present your results in front of a big auditorium like this. So today I want to talk about our most recent results concerning distinguishability of quantum measurements, and what we are mainly interested in this work were von Neumann measurements. But okay, this is the outline of the presentation. We will start with introducing the basic concepts we need to talk about our work. So we defined a quantum measurement, or a positive operator valued measure, denoted by mathcal letters, as a collection of non-negative operators such that they sum to the identity operator. And we can say that the probability of obtaining a label I from this alphabet gamma is given by this formula. So it's just the trace mi and some quantum state rho of our system. And we can view these measurements as. Excuse me? Yes, because we want to emphasize that we restrict ourselves to finite dimensional spaces. So it, and that's space. No, complex Euclidean space. Okay, Bert, yeah. Bert, yes. So it's finite. Okay. Okay.
Because we are human beings and artificially old, so artificially intelligent.
Okay. And with every measurement defined in such a way, we can associate a quantum channel that returns what is basically a classical state, so a diagonal state, with the probability of obtaining the label I as the ith element of the diagonal of the quantum state.
It's arbitrary name, right? Why is diagonal in this language called? I mean, why should I distinguish classical for something? It's just there is this huge table of measurement results of the measurements. So it's just a name that if it's diagonal, then I call it classical, right?
Because in a way.
You said quantum to classical. So
yes, because diagonal quantum states behave in the same way as.
There are no quantum states. There is a set of operators n.
Okay.
And you do all sorts of these, calculate all sorts of these traces, right?
Right.
So you have a huge table of those traces, and out of the blue sky, you call the diagonal in that space quantum to classical channel. Why? It's just a name.
It's just a name, right?
Okay, but there is something behind this name. Okay, definitely. So far. Okay, but probably it will be clear later. No problem.
And what should answer this question, why it's called quantum to classical, it's because when we try to distinguish two such states, is that they behave similar to classical probability distributions, and we can use the same concepts we use to distinguish classical probability distributions. So what's our setting? We have two possible measurements, m or n, and and we can prepare any input state into that measurement and perform one of these two denoted by X. And
because a measurement was a set of M's.
yes, it's a...
So now you call the measurement X is
No.
a set.
Yeah. M.
So the word measurement is now used at least in two different...
It's a bit overloaded. We can see it in two ways. One as a set of operators fulfilling this property, and in other sense as a quantum channel that maps maps states to diagonal states.
Yeah, but then there was this capital X, which is at two measurements M. There's just one M. So
Yeah, one M and one of two measurements, M and N. We are given a box labeled X, and we have a promise that it's one of the two. It's either M or N inside.
So there are two sets of operators.
Yeah,
M
yes,
and N.
yes, MI and NI, yes, exactly. And we want to tell which of these operations the black box performs. So we are allowed to prepare any input state we want into the box. And using the output, we want to decide whether X is equal to M or X is equal to N. And as a simple example, if we denote M with such a set and N with this set, and if this condition if there exists an I for which this condition is fulfilled, we can choose the state row to be.
Therefore, we know something about M and N.
Yeah. We know these measurements. We know these measurements, but we don't know which one. We know it's one of these two, but we don't know which one. Yes. No, it's if. It's just an example. We can say that we can notice this immediately. If this trace is equal to 0, we choose the input state proportional to this operator, because this is a positive operator. We just need to normalize the trace.
How can I choose it if I don't know what is M?
No, we know.
You know those assumptions.
Oh, yeah.
Once more, you know both these sets.
Yeah.
M and N, you know them. Okay. Otherwise, you couldn't decide whether they are orthogonal in the same.
Which to distinguish whether it's M or N? This is the question.
But it does
You
seem
know
to
this M and N. that this
it does seem to depend on
It
the
is
order,
written at the very
orders,
beginning.
on the
It was
labeling.
written. We know that
Yes.
with one to measure.
So how do you label M and N in such a way that you can identify the...
At this point, we don't concern ourselves with this. We are given a black box, and we are given the promise it performs either this or this, and the label is, and the order is decided by someone else, by someone who gave us the box. And
So it has no objective meaning, the labeling.
the labeling,
Whether this is 1 and 2 and whether it's the other way around.
yes, in principle, if you permute the order, the results can change. If you permute the ordering of...
Everything depends how I label.
Yeah.
That doesn't make sense. If it depends on the arbitrary ordering, how can you associate it?
I don't- No.
No, it does
That's-
depend because there's MI and NI with the same I.
So if there
Exists.
exists
Yeah. If yes, if there exists.
Okay, so we should do it like this.
If there exists.
I such that
Yeah. At least one. At least one. If there exists at least one I.
then this problem is simple.
Yeah.
This is an example of a simple problem.
This is yes. This is the simplest setting. If we notice that these two are orthogonal, then we choose the input state proportional to 1.
If I use the Greek letters to label M and the Chinese characters to label N, what is this meaning that how can I identify the I?
You can
Yes,
take
good.
them in order.
There. In some order.
But if ones are Greek letters and other are Chinese characters.
So it probably should be the condition that if MI and J, if there exists a pair IJ, that
Yes.
MI and J is equal to 0, then you try all MIs, and if you
Yeah.
find one that is 0,
Yeah.
It's a different.
Ah.
Okay. So that's now is essentially different than
Because there is some problem with indices. First you use I to label those measurements. You have M is equal MI.
Okay.
And then N is equal NI, which once immediately suggests that there is the same number of operators in both sets, which doesn't have to be true, yes?
No, in principle, no, but you can always fill the shorter set with zeros. Yeah, yes. Ah, okay.
As Lech mentioned, you can use I and J, then the statement can be reformulated
Yeah.
in a clear...
Yes. It should be...
Okay,
Yes.
And do we also know that every time it's like this, that MI and NJ are positive?
Once again,
Those operators have to be positive.
yeah, because M and N are POVMs, so yeah.
I was just making sure.
Okay. Semi.
So, but then, can we go back once? I have one more question. So, if I choose rho to be equal MI,
Okay.
and I do this measurement, so
Okay.
then shouldn't the conclusion be that X is actually N?
Once again, if you
Because you are saying that you are choosing rho to be equal MI.
okay.
So,
Yes.
so then the conclusion should be that X is N, I suppose, because then I'm measuring with this rho operator N, yes, to obtain this zero. How do I use it?
Okay, it's probably just a typo here. So, Now looking at this, yeah, you're right. Thanks, Adam. And why I said that these are somewhat classical states, because short detour to classical probability theory, given two probability distributions P and Q. By P and Q we mean vectors of non-negative numbers that sum to unity. The optimal probability of distinguishing them is given by this formula when this is just the normal vector 1 norm.
So, Łukasz, you have to remind us what is
Gamma.
capital gamma. First line.
It's just some alphabet, some set of symbols, and these vectors tell the probability of occurring of each symbol in the alphabet. Gamma can be gamma can be 0, 1, 2. It can be. Yeah.
What is the meaning of this arrow?
It's a vector of probabilities that sum to unity.
What is that meant?
Because this is
It's
this matrix.
Łukasz, I think the parenthesis there is misplaced, right?
what is misplaced?
The parenthesis, it's max sum of differences. You don't sum just one pi minus qi, but you sum the differences, right?
Yes, you sum the differences.
Yeah, but
You
the
sum.
parenthesis is wrong.
Yeah, but the parenthesis is to show that the entire sum is maximized, not just one element. Yeah, I understand. Maybe there should be another one.
You sum only pi, but you should parenthesis, but you sum actually you sum the differences, right?
Yeah, you sum the differences. Because this is just the sum of the absolute values of the differences, and it can be shown, it can be rewritten like this, so we get rid of the absolute value of the differences. And that's really helpful. And in our case, we can arrive at a very similar result where this part here is exchanged by the spectral norm of the difference of the operators. So instead of, and the max is over all subsets of gamma of our input alphabet.
So now you assume that there need to be the same number of operators in each set.
Yes, but you can always fill with zeros.
What is the meaning of this index infinity?
The largest singular value.
So what does it, if you have a maximum, why do you need to say something about infinity?
Because the maximum is norm
Infinity.
in mathematics. It's the common
Okay.
Ah, okay. So instead of maximum, you could write the.
Yes.
I'm sorry, can somebody explain?
Yeah. Instead of writing max, you can write infinity because in mathematics, the measure with the sign infinity means that it is.
You
Oh.
have there are two of them. So why there are two of them, max and infinity? This is a double infinity.
No.
Please explain again.
No. The max is performed over all subsets of gamma. So over all subsets of the set of operators. And we get an operator that is a sum of this form, where I is taken from this subset, and this just denotes denotes the infinity norm, so the spectral norm of an operator.
So one is maximum. You choose different indices
Yeah.
ij from this set delta. For each of those, you define such an operator, sum of mi minus mj. For such an operator, you calculate its norm, which is called in mathematics infinite norm. So practically, it's larger singular.
Okay.
And you look for the maximum of all those. Which is
Yeah.
Gamma in
What's more? What is gamma?
Yeah.
Okay, let's
It's-
go to the first aspect. Since you asked
But in classical case, I understand what
n
is
points
gamma.
are maybe
Yeah.
like a set
So-
of n numbers, like 0 and 1.
Oh, yeah.
If gamma has two indices.
Gamma is just the set of possible outcomes.
So gamma na przykład w kwantowej mechanice, bo in the quantum mechanics it could be for example +1 or -1 or +1/2 or -1/2 if you have a space. Okay?
Yeah.
Set of outcomes, which is discrete in this case.
Yes. Everything is discrete and all spaces are finite dimensional.
So you can always think that you are measuring some speeds, okay, along some axis, okay, and then the gamma is the possible outcomes of this measurement, okay. It could be highest speed, for example.
Yes.
From -j to +j, okay. This is gamma. This is the set of possible results of measurements, okay.
Yeah, can I ask a question? Because not everybody here is an expert. Just coming back to the classical case.
Yeah.
You have a coin and you flip it, say once. It's not the very, it's
Okay.
too few, but say once. And you know that it can be either a coin which is correct, so it has one half head or tail, or a false coin which is 3/4, 1/4 head
Okay.
of tail. Can you explain how you calculate the optimal probability of guessing which coin it is?
Okay, so so in this case, our alphabet gamma is just heads and tails. And if we have, let's say we have P is the fair coin, so it's 1/2, and Q is the biased coin, so it's let's say 3/4 and 1/4. So, and according to this, we just take that the P opt of guessing is given by
3, 7, 3, 4.
yeah, it's actually 4. It's 3/4 and 1/4. So it's 1/2 plus 1/4 of, and here we have this minus this. So that's 1/4. And this minus this is also 1/4.
This is the sum, yes? P minus Q. Right?
Yeah.
It's a sum
Yeah.
of
Yeah, sum of absolute values. Yes. Yes. So this is 2/4. This is 1/4. So this is 1/2. So 1/2 times 1/4. It's 1/8. So it's 5/8.
And what is the interpretation now of this number? What does it mean, this P opt?
The interpretation is.
This number.
Excuse me.
Interpretation.
Yeah. So if we perform our experiments and obtain some empirical probability vectors, then this is the correct, we have these coins, obtain some probability vectors, this is the probability of correct distinction between these coins.
Actually, may I say something? It's
yeah.
Maximal likelihood method. So if you observe
okay.
then you would say that it is from the second solution, because the probability is higher. If you observe
Okay.
A, then you said that this comes from this third coin.
Okay,
So it's a
and
maximal
5.8 is the probability that you get.
Okay.
Very good. Thank you.
But you assume that you have some knowledge of P and Q.
Yes, yes, yes. This is a given promise. Yes.
There are two sets of measurements between you and But once again, so let's go to the first assumption, maybe it was
Yeah.
But you cannot get probability vectors from several experiments, because you need infinitely many experiments to get the probability.
Can-
But you know how your vectors
Yes, you know two measurements, so two sets of probabilities. You know set M and set N. And you only want to distinguish. Like example of leg is perfect. Because they are all this
That's
from
it.
another
I was questioning that you know this from an experiment.
No, you
No.
know it from some other guy.
Okay.
Yeah.
These two coins, like the leg takes or fair coin or unfair with
Okay.
such a bias.
Yes, okay. But
But
not
still
from
a nice
experiment.
example, yes.
Not from experiment.
But that doesn't allow me to distinguish if I just throw the coin.
Many
Yeah,
times
that's-
with such probability.
Probability.
Infinitely many times.
Then with such a
I will
probability.
be tired. It would be irrelevant, but this is whatever.
Okay, so let's allow speaker to continue.
And this was all somewhat classical approach, because we took our black box, prepared some input state, observed the output, and tried to decide which measurement was performed based on that output. But of course, in the quantum case, we can do a bit more. We can, here's the picture. We can perform such an operation. So now this is our black box containing the unknown measurement, and here we have some additional system. We put one part of the system through the unknown measurement, obtain some label I, and based on this label I, on this additional part, we perform another measurement that gives us an answer which of these two measurements was performed. And what do we call here? It's entanglement-assisted discrimination, because as the name suggests, this input state will generally need to be entangled to help us achieve better probability than this classical limit. And from now on, we limit ourselves to von Neumann measurements and introduce the following notation. So one set of the von Neumann are just projective rank 1 measurements. So all the operators in these sets are rank 1 projectors that sum to identity. And as such, we can label them using some unitary matrix U, because it's just the rotation of the canonical basis. And without loss of generality, we can assume that one of the measurements is performed in this computational basis.
What is the meaning of this index I?
It just means overall relevant I from 0 to dimension minus.
As the I in the Brian cat?
Yes. It means just a set of the form U00 U dagger, U11 U dagger, and so on, up to U D-1 D-1 U dagger.
So P U depends on I, does it?
No.
This label I
Eh?
is that I
It denotes the entire set.
set of integers,
Yeah.
capital.
Yes.
It's a collection of these things.
P U is the collection.
P1 is a collection of a projection of a star I for all possible i's. There is a missing epsilon
Yeah.
I.
So it's like a basis and you rotate it by
No,
U.
it's missing this little epsilon and a capital I.
No, but do we know that those projection operators are orthogonal to each other?
Yes.
If I have I and j, they are orthogonal, yes?
Yes.
This is some kind of basis.
Yeah. Yeah, this is just a rotated basis, another rotated basis. And in this black box we have either PU or P identity. And our aim is to distinguish which one with optimal probability.
So all we have projection in a given basis or in a rotated basis?
Yeah. And of course we have a bigger problem now because we have to optimize over the size of the additional system. We have to optimize over the all input possibly entangled states, and on the final binary measurement, which tells us either there was PU or P identity. This can be this can be achieved using semi-definite programming, which is outside the scope of this presentation. So just as a side note, and
I do not understand what it means.
Yeah, it will be explained on the next slide.
Programming will be explained.
Yeah, yes, briefly, and it will be explained at on our file. For those of you familiar with mathematical programming, linear programming, it's just a bit further, so to speak, and we will show that. And this is just a generalization of the somewhat classical result when, again, it's similar because it's the diamond norm here is just a distance on the set of quantum channels. It's a way of defining a distance on the set of quantum channels. It's called the diamond norm or the completely bounded trace norm. And it's defined in the following way. It's maximum over all input states of norm equal to 1. Maximum of the one norm of the extended operation, of the operation on an extended system. And we also know that if this operation phi preserves the hermiticity of X, this can be done, this maximum is achieved on a pure state. So in other words, this X is rank 1. What?
Why this norm has an index I outside?
It's
one. It's one. It's trace norm.
There are several norms in operator space. Okay? So finite dimensional,
This is one.
and they have the different symbols to use.
I overlooked it. I thought it's I.
Maybe you can write a definition of a P norm.
Okay.
Everyone will understand what is the meaning.
No, because then there will be P and people will ask what
No, but that P is a right norm.
It's not P because P is used here.
It can be P.
It's a one norm.
So the one norm. I don't know if this explains more than it convolutes more at this point, but it's formally like this.
put this one.
Ah,
Double, yes.
yeah, of course.
Okay. Is it a generalization of taxing method?
Yeah. And again, to recall our setting, we are interested in finding this state and maybe tell something about the dimensionality of this state. And we arrive at the following problem and at the actual solution, because if we minimize this quantity, which is basically the sum of absolute values of the diagonal elements of such an operator, given that rho is a quantum state, then we can write this this quantity, this diamond norm, that again gives us a bound on the probability of correct distinction, we can write this in such a very nice form. And of course, this cannot be solved analytically, but this can be solved efficiently for given U, can be solved very efficiently using well-established numerical libraries for convex or for semi-definite or convex. In this case, it's even convex problem. And the final part we would be interested in is the dimensionality.
So the sum is the minimum of the number, right?
Yeah, it's yeah.
Possible U.
No, U is given. U is given here by this measurement. What's?
So it's over row.
Yeah, it's over row.
So let's consider the following situation. We have two devices. One measures, these are Stern, Gerlach, or whatever devices. One measures the spin along x-axis and the second about z-axis. Okay. So definitely these are both are in two-dimensional, acting in two-dimensional space, and there are different bases. One base is connected with the choice of z-axis. The second with x-axis. This is a rotation. This u is given, and this is this rotation, which rotates z-axis into x-axis. This is the u, and this is given. And now we want to discriminate. I put some input to this one and to the second, and one or to one. I have one such a device. I don't know whether it measures spin y, spin z around z direction or x direction. Okay? And I obtain some measurements, some results, and then I want to decide whether I measure whether my device was directed along z-axis or along x-axis. And this is the story. Okay? The simplest possible.
Yes.
The simplest possible. Then you have the generalization, because this box can perform many different measurements. Okay, and then you will discriminate with the set of measurements which are performed by each of these devices. This is the whole story. But these devices are given. Okay, so you know what is how the first one is in relation to the second one. It's given by the rotation of this basis in which you make this projective operations. Okay, if you have enough number of projections, you can identify with an orthonormal basis in this space. Okay, and then you rotate this basis from one device to the second device, and you want to discriminate between the devices. This is the story which we want to do.
I have a question.
Yeah.
What is the advantage between the previous scheme, which you called classical, where basically you did not use the entanglement, and this entanglement assisted? So do you get better probability error discrimination?
At least not worse. At least not worse. It depends. For some U, we identified some classes of matrices U that can be distinguished optimally without the need for entanglement. But in the general case, you need some entanglement to, and then you outperform the classical approach.
Is it like a naive question? So can you prove it somehow from the properties, some relationship between the trace and diamond norms? Is there anything that can help on the mathematical side?
What do you mean relationship between?
Usually norms are somehow related, yeah?
But yeah, you can give bounds.
Exactly.
But these bounds are usually very coarse, and I think they didn't help in this problem. Okay.
So, pardon, to sum up, in some cases you have the advantage, in some cases you are at the same error as without entanglement.
Yes.
Actually, you have an example that for large dimensions, if we consider Fourier matrix,
Yes,
U is a Fourier matrix of a prime dimension, then you cannot perfectly discriminate it without entanglement, but if you use entanglement assisted procedure, then you can distinguish them perfectly.
Perfectly mean that the probability of error is zero, strictly.
Yes.
Strictly.
Yes. And one final thing is the dimension of this additional space here, we have reasons to suspect, but we were not able to formalize this, that in the vast majority of cases, this can be chosen as a single qubit. When you need entanglement, this can be chosen as a single qubit. We were not able to prove this strictly, but as long as you don't have some very strange degeneracies in the spectrum of U, then we are very certain that it's a qubit. Okay, so this was one approach, but okay.
So, do you control what kind of entanglement do you need, or is it just all backed up in the diamond norm?
It's all backed up in the diamond norm. And this setting had a probability to give us a wrong answer. So what if we want to construct a procedure which tells us either when that we want to be certain, if it gives us an answer, then we know it's true. So this is called unambiguous discrimination. And the simplest setting is as follows. So we again have a black box that performs some measurement. We are allowed to prepare any input state into the black box. But now, based on the outcome we obtain, we have three choices. We say either it was one of the measurements or the second, or we throw out the results. So it's trash. So it's probability that the procedure will say, well, I don't know. But if we obtain an answer, we know it's correct. It's the correct one. And this is a simple example for a qubit. And so if we have a qubit, and again for Neumann measurements, then it all sits in the off-diagonal element of this matrix. And this result is a bit strange because if the modulus of this element is strictly equal to 1, then the probability is 1. But if it's below 1, then we have 1/2 of that element. But of course, in quantum case, we can again do better and use entanglement. So we again have one part, we perform the measurement on one part, obtain a label I, and on the remaining part we perform some measurement, which now has three possible outcomes. It was either one of the measurements or the second, or we throw out the result because the procedure failed. And in the general case, it can be written like this. So it's again some minimization over the diagonal of such an operator. But what's interesting in the qubit case, it reduces to something like this. So we have a very nice and simple result. And finally, what if we want to do, we are given a black box and copies of a black box. And how can this help us in distinguishing measurements? So we have two possibilities. We either have a parallel scenario. So we prepare a huge input state on systems 1, 2, 3, up to n+1. On the first n systems, we perform the unknown measurement, obtain a set of n labels. Based on all these labels, we perform a final measurement here, and based on this, we arrive at the decision. Or something vastly more complicated, the adaptive procedure. So again, we prepare the system of the same size as before, and on the first system, we perform the measurement. We obtain a label I1. Then based on this label, on the remaining part of the system, we perform some unitary operation. Then after that, on the system number 2, we perform a measurement, obtain a label I2. Based on these two labels, we perform on the remainder another unitary operation, and so on and so forth. And until at the end, again, we have all these measurement outcomes, I1 to IN, and we are allowed to perform one final measurement on the n+1 system and arrive at the decision. Some first intuition would suggest that, yeah, this should be better because we have a lot more possibilities, a lot more operations we can do. Actually, what we found that the parallel approach is optimal. So we don't need all these operations. You can just get rid of them. Yes. Yes, the boxes are, yeah. If the boxes are not the same time, then you have a problem. Yes. Or you can use the same box multiple times. Exactly. If you're given different boxes, then that's a completely different question. Or if you don't know, you don't have a problem with what's in the box, right? These are different questions. And again, we arrive at the very similar results, but what changes from the previous approach is that we have some larger row and we have a tensor power of the matrix U here.
And there is absolute value, right?
Yeah. Yes, yes. And this gives us actually a nice geometric interpretation of these results. Because consider that lambda 1 is an eigenvalue of U, chosen to be, and without loss of generality, we can assume it to be equal to 1, and lambda d is the eigenvalue with the highest argument, with the highest complex argument, so it's somewhere here. And if we draw it like this, then actually the diamond norm of these two measurements is given by this chord, and the probability of unambiguous discrimination is given by this section here. Then, if we perform twofold discrimination, meaning that we are allowed to use the unknown measurement twice, what happens? This happens. This angle gets twice as big as before. And the interpretation still holds, but then, when we are able to perform one more time, the angle gets bigger than pi, and suddenly we have perfect distinguishability in both cases. Whenever the angle gets bigger than pi, the diamond norm gets equal to 1, and the probability of ambiguous discrimination is also equal to 1. This is based on these two quite recent works. And thank you for your attention.
So are there any questions?
Is there a practical lesson that an experimentalist, if there is a practical lesson that an experimentalist can obtain from your results, how would you tell an experimentalist to improve their methods of making measurements?
What we are trying to do now is to implement these procedures on existing quantum computer architectures and see if
let's forget about the quantum computers.
Okay.
I am an experimentalist. I wanted to learn whether I can improve my measurements by using your results. For example, I'm measuring the scattering cross-section, whatever, that gives me, or
possibly make measurement on basis Z and rotated basis X. Make it
simpler. I think the main takeaway message here is that well, yes, of course. The first one is use untangled states, and the second one is that there's no need for adaptive procedures like this. That doing some measurements in parallel is optimal. And well, I'm not an experimentalist, obviously, but
you people don't talk to experimentalists to learn what they need.
That's very safe procedure.
Sure.
Okay, more questions?
Could you comment how do you want to implement it? Could you comment how do you want to implement it in quantum computer architectures?
Well, actually, we want to implement it on the Rigetti architecture now. What they provide. What they provide is I think it's a 9-qubit at this point computer using the gate model. And the main problem, there are some technical problems, of course, but the main problem is this these controlled measurements. And we are implementing this using post-selection. we post-select just on the obtained labels, and on the other hand, you need multiple tries. It introduces a lot of noise, and that's one point. And the other thing is the careful handling of the input state and preparation of the input state, because also you have to reduce the number of 2-qubit or multi-qubit interaction, because it's also kills the performance.
Yeah, but what kind of problem it's going to solve, this implementation?
We're not aiming on solving any specific problem. More what we aim at is somehow benchmarking that architecture and showing somehow measuring the number of errors it introduces in a more complicated procedure.
Any other questions? Okay, so I also have a question. So
okay.
As I understood, the scenario is that you have two measurements and you don't know which one is performed, and basing on some data you want to decide which measurement was done. So what is the, is it, can you connect it to any specific experiment where you, I don't know, measuring something and you don't know what you are measuring? What is like...
well, as I said, this is a difficult question for me because I'm not an experimentalist, and
sorry, but you can perfectly imagine that in the experiment you don't have a full control over what you are performing, and you want to know how far away you are from the target measurement. I think this is a perfectly understandable application, just like with the state discrimination. With the state discrimination, you try to produce a state. Of course, you have some experimental errors, and then you want to see how far away from your target state you are. But this is the dual picture from when you move from states to...
Yeah, I understand, but okay. I just wanted to get some examples so that people are more into this.
I think the Marek's example, so you try to implement some sort of rotation, and you don't have full control over the rotation. It lands in a randomly distributed angle, because your motors are not perfect.
Mm-hmm. Okay, anyone else? Then let's thank Łukasz once again.